Our speaker today is Matt Hastings from Microsoft Research, and he's done a number of amazing things in condensed matter physics and quantum Shannon theory and quantum algorithms and complexity. So today he's going to be talking about some recent work he did on the power of adiabatic quantum computation without a sign problem. So take it away, Matt, and thanks very much.
Okay, yeah, thanks for the invitation. Yeah, there's a change in topic, as you just noticed. I'm going to talk about adiabatic computation with no sign problem instead of what I said I was going to talk about. I just felt I was more prepared to give this talk. And I thought people would still be interested. And yeah, please ask lots of questions either in the chat or just verbally or whatever, because that's the whole point of holding a seminar rather than just recording a solo talk just by myself, right? So please ask a lot of questions. So I want to talk about the power of adiabatic quantum computation with no sign problem. So let me start, and I don't think this is necessarily the best way to introduce the topic. I don't think it's really the motivation that should be our motivation for the topic, but since it's a familiar one, I want to start with a certain motivation, which is the adiabatic algorithm. So the adiabatic algorithm was proposed by, and I've got a whiteboard. Can everyone see my whiteboard share? I just wrote H sub S on it. I'm about to start writing some more stuff. Okay, good. I see a thumbs up so people can see it. So I'm about to start writing so the adiabatic algorithm was proposed by Farhi and collaborators years ago, and it's an algorithm for doing combinatorial optimization. It's a proposed quantum algorithm for doing combinatorial optimization. And the idea in its simplest form is something like this. You have a Hamiltonian, and I'll write H sub S to indicate that the Hamiltonian depends upon a parameter S. S will be a scalar, a real number in between, let's say S in 0, 1. And the Hamiltonian is the sum of two terms. And the first term is what we'll call the driving term. Oops, I want to write 1 minus S there, minus 1 minus S times X. And what I mean by 1 minus S times X, well, 1 minus S is just something that starts at 1 and goes down to 0. And X will be, we'll have a system of qubits, and X will be the sum of the Pauli X term on every single qubit. So it's just a Pauli, it's just a transverse field on every qubit. And then the second term in this, let me just shrink this down a little bit to get a little more room to write. Second term in this will be plus S and our H sub Z. What is H sub Z? H sub Z is the objective function of your optimization. So you imagine that you have some optimization problem, which is a function of bits, classical bits, and you promote that objective function to a quantum Hamiltonian. So you just take the operator that's diagonal in the computational basis, and its value is that objective function. And so what this Hamiltonian H sub S does is it interpolates between initially this transverse field, and you, as S increases, you turn off the transverse field and you turn on this objective function H sub Z. And if you stay in the ground state during the entire evolution, at the end of the evolution, you'll wind up in the ground state of this H sub Z, which will be minimizing some objective function, which is your goal of your combinatorial optimization. Now, how well does this work? Initially, there was some excitement based on small size numerics, and I think this is a lesson for extrapolating from small size numerics, because it's very hard to do simulations of quantum systems on a classical computer. It's the whole reason we want a quantum computer. And so if you're limited, in this case, to maybe 20 or 30 spins, it's very hard to, if you're doing a full simulation, it's very hard to do to really extrapolate much. And even when you use things like quantum Monte Carlo, when you can do bigger systems, it's still hard to extrapolate. And so there was initially some optimism, but I think it's now become very clear that, that if you just plug in for H sub Z some unstructured objective function, meaning something like that came from a real classical optimization problem that you really cared about, either a random instance, which was just some toy model, or a actual like meaningful practical objective function. What will happen is, unfortunately, that the gap becomes small. I'm getting a little ahead of myself. Sorry, let me say this in a little bit the right order. So in order to stay in the ground state during this evolution, in order for this algorithm to work, what you want is that the gap between the ground state and the first excited state never becomes too small. So you start out, when S is 0, you start out in the ground state, which is this transverse field problem. There's a gap to the first excited state. And it's easy to prepare the ground state at S equals 0. It's just a whole bunch of spins pointing in the plus direction. And as you increase S, the gap may change. And if the gap doesn't get too small, if it's only polynomially small, then you can, in polynomial time, evolve this Hamiltonian from S equals 0 to S equals 1 and stay in the ground state. do it adiabatically on a quantum computer, and then solve your final objective function. Unfortunately, as I said, the evidence is now very strong that that doesn't happen, that for most problems you will have a tough time remaining in the ground state. So this is the adiabatic algorithm. Sorry, I said that a little bit out of order, so, but I think hopefully if there's questions, let me know. But still, you know, we may wonder about the power of this model. We may wonder about the power of this kind of computational model where you're doing adiabatic evolution between two different Hamiltonians, or perhaps along a path of Hamiltonians, where it's easy to prepare the initial ground state, and it's you then do this adiabatic evolution, and then you measure some property of the final ground state. So you're interested perhaps in a problem where you start with some Hamiltonian where it's easy to prepare the ground state, you do an evolution, and then you end in some final Hamiltonian. You require that the gap between the ground and first excited state only become polynomially small, and then at the end of the evolution, you measure some property of the final Hamiltonian. So there's an old result by, I don't remember all the people on it. I know Dorita Haranov is one of the authors. I don't remember all the authors. That if these two Hamiltonians that I wrote as S and this one, oops, I wanted to do that as a last out to grab it, but anyway, let's try to see, can I undo that? Okay, this one, if these two terms here and then this other term here are both just the X and the H sub Z term are arbitrary local Hamiltonians on qubits. So where the first one is something you can prepare efficiently, the ground state, but they're both some arbitrary local Hamiltonians. There's a result of a Haranov collaborators that this is equivalent to BQP, that first, this evolution can be done in BQP. You can, oh, okay, Andrew just put up the reference, thanks. You know, we can simulate this evolution on a quantum computer because we can simulate Hamiltonian evolution on a quantum computer. There's a number of technical things you need to assume. In addition to the gap being only polynomially small, there needs to be bounds on how quickly the terms in the Hamiltonians change, bounds on how large the Hamiltonians are, bounds on the sparsity of the Hamiltonians, and so on. But given all those technical conditions, you can simulate it on a quantum computer using any of a number of standard simulation algorithms. And conversely, this is fully capable of doing anything in BQP. Any problem in BQP you can do by doing this evolution and then measuring some suitable function of the final Hamiltonian. But this particular Hamiltonian, the one that I've written here, has an additional property, which I'll call no sign problem. Sometimes the word stochastic is used, but I just don't like that term because no sign problem is an older term. It's earlier, and stochastic just sounds a little funny to my ear, but some people call it stochastic. So what is this property of having no sign problem? So the property of having no sign problem, now I'm going to drop the subscript S. This is just a property of a single Hamiltonian. This is a problem of every Hamiltonian along that path. Is that if I take the Hamiltonian H and I write Hij to denote a matrix element between basis state I and basis state J of this H. And this is a basis dependent statement. And in this case, the basis will be the computational basis, the 0, 1 basis of qubits. That H sub Ij is less than or equal to 0 if I is different from J. All the off-diagonal matrix elements are non-positive. So it's a very old theorem. I think it's about 100 years old now, the Perrin-Frobenius theorem, that if you have that property, the ground state of the Hamiltonian can be chosen to have all its amplitudes real and non-negative. So you can sort of get rid of all the sign structure in the ground state. The ground state can be chosen so that all its amplitudes are either 0 or some positive scalar. And this just follows from an easy variational argument. If you write down any state, I can just improve its energy by replacing all the amplitudes with their absolute value. And that will always improve the energy of the state, or it won't hurt the energy of the state. So this particular property of having no sign problem sort of suggests that this Hamiltonian is like less quantum in some way, more classical. You can, for example, interpret the ground state as being like a probability distribution, and you don't need to worry about whether there's some sign structure. Sort of, if you want to be very heuristic, you could say there's only constructive interference, but there's no destructive interference. And this no sign structure is responsible for the existence of some powerful simulation algorithms based on what's like quantum Monte Carlo. So what are these algorithms? So imagine we have some Hamiltonian H that has no sign structure, no sign problem, sorry. And you want to compute typically, for example, the partition function. So a trace of e to the minus beta h, where beta is some scalar. And as you take beta large and positive, beta is like the inverse temperature. As you take beta large and positive, e to the minus beta h will converge to a projector onto the ground state up to a normalization. And by taking this trace, you can get the ground state energy. And it's sort of a general principle in statistical physics and computational physics that if you know how to get this partition function, you know how to get everything. I'm not sure if there's fully a formal computational complexity statement to that, but because what you really need to be able to do is to also compute derivatives of the partition function to get everything. But in general, if you can compute this partition function, you can work out whatever you want to know about the problem. How would we go about computing this partition function? Well, the nice thing is that there's a path integral method of computing it. It's the usual kind of path integral. There's a couple different ways you could do it. You could imagine, I'm going to draw two axes here. So sort of a x, or x is really space, but it's some configuration. It's some arbitrary configuration. It could be the basis states of the problem. And a time axis. I'll write tau to sort of remind us that it's imaginary time. And that tau axis goes from 0 up to beta. And what you do is you sum over trajectories, which are trajectories paths x of tau. So you have some path that stays in some configuration, that jumps to some other configuration, stays in that one, jumps to some other one, and so on. And it does have to be periodic, so it has to return to the same one because we're looking at a trace. And each of these paths comes with an amplitude. And it's a standard result that you can work out the amplitude that every time it does one of these jumps from some configuration to another, like that one, oops, like that jump, you pick up some factor that depends upon the matrix element of the Hamiltonian between those two states. So if the left half that was state I and the right half was state j, you'll pick up a minus hij. And then you also pick up, for this evolution along those vertical lines where you're staying in a state for a while, you pick up a factor of e to the minus the diagonal entry of that state times the time you evolve for. So there's a simple prescription that you just sum over all these paths where you stay in a state, jump, stay in a state, jump, and so on. And you have an amplitude that depends upon the Hamiltonian. And here's the crucial thing. If the Hamiltonian has no sign problem, that amplitude is it's non-negative, it's 0 or positive. So in order to compute this partition function, well, for any quantum problem, doesn't matter what h is, you can have some path integral for it. But the great thing here is that the path integral is a sum of non-negative numbers. And that's much easier to do than a sum of positive and negative numbers. Like if you had to sum positive and negative terms in the path integral, this is what's called a sign problem. It could be the case that there's a very big positive term and a very big negative term, and they cancel out and give something that's small. But summing positive numbers is much simpler. And from a formal computational complexity statement, there's results of Bravi et al. And collaborators that this changes the complexity from, I think it's something down to, I think it's within AM and conjectured under de-randomization assumptions to be an NP. But in any event, you can just intuitively see that it's an easier sort of thing to do. And there are algorithms, just like if this H were classical, if this H in here were classical, in the partition function were classical, that is a diagonal Hamiltonian, this would just be ordinary classical statistical mechanics. And there's algorithms based on Markov chain Monte Carlo. So you would have that for each configuration, rather than path in time, but just each single configuration, there'd be some energy for that configuration. You'd want to sum over all configurations with some amplitude, with some probability. And there's these Markov chain Monte Carlo algorithms, which attempt to sample from configurations with a probability proportional to that weight, that Boltzmann weight, e to the minus beta h. So as an example of such a thing, you might imagine a system of spins, up and down spins with some Ising model, and there's algorithms that try local flips. Like you take a single spin, you try flipping it from up and down, up to down, and you accept or reject with certain probabilities. Building some Markov chain, and you construct those probabilities to obey detailed balance, and so that the stationary distribution is the Boltzmann distribution. And if you can equilibrate that Markov chain, you solve the classical problem. Well, here it's almost the same thing. You have, rather than a configuration, you have a path, but a path can just be thought of as like a configuration in a bigger configuration space. So you have a space of paths, and you can imagine a Markov chain algorithm that does some updates. Like, oh, you might take a path and you might imagine, okay, I'm going to try adding on like a little move where it sort of adds a little like boop out to the side and back, or, like make a little longer or shorter this way or whatever. You can just imagine all kinds of little local update moves and ask, well, if those local update moves can equilibrate the Markov chain, then things get, then we can solve the problem. Now, we definitely don't always expect that those kinds of Markov chains can be equilibrated. Even for classical Hamiltonians, we know that they're classical Hamiltonians where finding the ground state is NP hard. And for those Hamiltonians, the Markov chain is typically not going to be able to equilibrate. We'll often get stuck in some sort of false minima and be unable to find the true minimum of the Hamiltonian. And the same thing can happen for these quantum things when you're summing over paths. You can get stuck in false minima. You can be looking at the wrong kind of path where you should be somewhere else. But now comes the combination of the two features, which is what I'm going to talk about. If we look at this adiabatic algorithm of Fari, it's got these two properties. It's got adiabatic and it's got no sign problem. And we might ask, what happens to the power of the Hamiltonian of the model where you combine it? We know that adiabatic means it's in BQP. No sign problem means very plausibly, even for a single value of the Hamiltonian, single S, it's within, plausibly it's in NP. So this combination is some quite restricted thing. And you might imagine that there would be an algorithm that combines those two ideas of adiabatic evolution with these Markov chain Monte Carlo. You could think that, well, maybe what I'll do is I'll be able to equilibrate the Markov chain because I'll follow its evolution as the Hamiltonian changes. I'll equilibrate it first for some value of S. I'll change S a little bit. I'll try to re-equilibrate it. I'll change S a little bit, try to re-equilibrate it, and so on. And hopefully, in that way, you will avoid the issues with equilibration. And people have made use of this in practice, simulating like the D-Wave device has been, like Troyer and Katzgrab and collaborators have done a lot of work on simulating the D-Wave device or simulating something that mimics the D-Wave device using this kind of quantum Monte Carlo algorithm. So the question really is, like, what I want to address is, what's the ultimate computational complexity of this model when you combine adiabatic with no sign problem? I should emphasize also, I said at the start that there's strong evidence that the adiabatic doesn't work just for arbitrary optimization problems. If you just put in some like practical objective function, I think that's all those arguments still apply if you put in local driving terms that violate a sign problem too. So I don't think the sign problem is meaningful there as to why it has a problem working. But in fact, if I gave the short path talk that I meant to give, you might see some reasons why adding those local driving terms without, why it's good to have no sign problem. But anyway, that's the problem I want to talk about. And the main result is that this combination of these things, no sign problem and adiabatic, is still outside the range of what can be classically efficiently simulated. That this is still something beyond P. It's still some interesting model. It's not efficiently classically simulable, even though it's not, almost certainly, there's no proof, but it's almost certainly not BQP complete, and almost certainly not, but it's some interesting intermediate thing. So that's kind of the statement of the problem. Let me just make sure, is everyone happy? Just pause for questions and comments. No. Okay. Everyone's happy. Good. Okay. So like I said, the main result is going to be that this model is not efficiently classically simulable. So this is going to be an oracle result. And I think this is probably a computer science audience, I'm guessing. So probably don't need to say too much about oracle results, but I will. So what does it mean it's an oracle result? Well, we're going to define, and I'll try to give some precise formulation, and you can look in the paper, in oracle that you ask, and it tells you things about the Hamiltonian, in terms of the Hamiltonian. So rather than given this Hamiltonian, this adiabatically changing Hamiltonian with no sign problem, in terms of a sum of local operators like Pauli driving terms and maybe Ising type terms or something, it'll just be given as this oracle you ask questions of, and we'll prove a lower bound on how many questions you need to ask in order to be able to solve a problem, which again, I'll try to define the problem a little more precisely. These kind of oracle results, when I first heard about this years ago, coming from a physics background, I kind of thought this was like a cop-out, that, oh yeah, the computer scientists use these oracles, but that's just because they can't solve the real problem. I mean, and to some extent that's true. The technology in computer science is nowhere near being able to prove that P not BQP, P not P space, but there are all kinds of oracle separations you can prove. So for one thing, you do it because you can prove it, but it is an incredibly powerful tool, and to help us understand these problems. And after now years of like listening to computer science talk about it, I've come to think, oh, it's the obvious thing you do. So I guess if you first think something is a silly idea and then you think it's an obvious idea, that means it's really actually a great idea. So I think this idea of working with oracles is something is really a great way to think about these problems in computational complexity. And one thing it does tell you, one thing it definitely does tell you, I don't give strong evidence that there's no algorithm to do it, but it does say, well, if you do have an algorithm that's going to, a classical algorithm that's going to work out properties of this adiabatic evolution with no side problem, it's really going to have to use something very structured about the Hamiltonian. It can't just treat the Hamiltonian as a black box, which is how most of the present algorithms do it. It can't just treat the Hamiltonian as a black box. Okay, so let me try to define what this oracle model is going to be a little bit better. So we'll have some oracle, and what you do is first of all, you can give it a value of s in this interval 0, 1, and you can give it a computational basis state. So you can say, okay, at s equals 0.5, computational basis state I, I'll just use some arbitrary label, I'll call it I. What are the other basis states to which H sub s has a non-zero matrix element? And we'll say, okay, well, these are the list, J1, J2, J3, J4, J5. These are the ones for which it has a non-zero matrix element to it. And these are the matrix elements. It will give you a list of the matrix elements and will tell you the diagonal matrix elements. That's what the oracle tells you. And you'll be promised a few things. You'll be promised that all these, that the H sub s is only polynomially sparse. So there's only polynomially many other J that this I will have a non-zero matrix element to. You'll be given some bound that the individual matrix elements of H sub s have derivatives that are most polynomially large. You'll be promised that the gap between the ground and first excited state is only polynomially small. You'll be promised all matrix elements are only polynomially large. That's necessary because otherwise there's no meaning to setting the gap to be only polynomially small. You need to set an energy scale. And you'll be promised also, you're told the basis state that is the ground state of the Hamiltonian H of 0. Now, that's a little bit different with this driving term. It's actually, rather than a single basis state that's the ground state at s equals 0, it's the superposition of all states. But it's easy to imagine a path that starts with a single fixed state, like the all spin up state, and evolves from that to the all spins in the plus direction state. So I'll just change the definition of the problem. It's an unimportant change and say you're told, okay, the ground state at the start of the problem is a specific basis state 0. And your goal is to compute. You'll also be promised that the ground state at the end of the evolution is also just supported on a single basis state. And your goal is to figure out what that basis state is, and do it with some probability. And even, some non-negligible probability, not even probably half, but like, let's say, better than exponentially small. And the result is that in this oracle model, there's no classical algorithm that can do it with fewer than n to the log n queries. All these polynomials are polynomials in n. N to the log n queries, which is super polynomial, but not much super polynomial. Now, before getting into this result, before getting into a technical result of no classical algorithm can do this, it's worth looking at the most commonly used classical algorithm and asking how you would defeat that most commonly used classical algorithm. That is this Markov chain Monte Carlo, partly because that's the most common one, so might as well think about that first, and also because the way to defeat that one, a lot of those ideas are used in the general result. So this is work. I see a question. What is the oracle here? What do you mean? The oracle is the oracle that tells you terms of the Hamiltonian. So the oracle is something you query to ask it for entries of the Hamiltonian. And you're given a number of promises about the properties of the Hamiltonian. Does that answer the question? Yeah, I'm not quite sure what the question is. I mean, okay, good. Okay, that answers the question. Good. So we're going to talk about how to defeat the Markov chain Monte Carlo. So this is work of mine with Mike Friedman, but many of the ideas are actually ancient ideas in condensed matter physics, because the problems, we're constructing models that have certain problems, but these are problems that people actually run into in practice before, so they're well studied. So what I want to imagine is a problem like the following. We're going to have a single site. Oh, when I say a site, sorry, this will be a single computational basis state. I'm going to draw a picture, and this picture is going to be sort of a pictorial way of denoting some terms in the Hamiltonian. And nothing's going to be hard in an oracle setting here, but this will defeat a certain algorithm. And I'm going to draw a figure 8. Now, what is this figure 8? Well, the figure 8 is going to have a lot of little sites on it. I'll draw a lot of little circles. But what you should imagine is, just fill it with circles. like that. So it's like two one-dimensional chains. And so there'll be some hopping element, some off-diagonal matrix element between neighboring terms on those neighboring circles on those figure eights, so the particle can hop around the figure eight in some way. And then there'll be this initial x, which is one more basis state. And then there'll be some dashed line. What is the dashed line? That's going to be one more coupling. And I'm just going to adjust two terms here. One term I'm going to adjust is the strength of that dashed coupling, and another one I'm going to adjust is the diagonal term on that site x, that site x. And I'm going to leave everything else unchanged in the Hamiltonian. And I'm going to start with the x, the diagonal entry on that x being very negative, and the dashed line being having no hopping. So then the ground state is just on that site x. So then what I'm going to do is I'm going to imagine a path, an adiabatic path, where first you turn on the dashed coupling, so there starts to be some tunneling between the x and the figure eight. Then I'm going to raise the energy of that site x, and then I'm going to turn off the dashed coupling. And if you focus on the ground state of the figure eight and the state of the x, this looks a lot like a two-level problem. That is, it depends what happens. If the energy of the figure eight is here and the energy of the x is here, I raise the energy of x only up to here, at the end the particle will stay on the x, but if I raise the energy of the x up to here, the particle will move to the figure eight at the end. So the final state will depend upon how does the energy of this x compare to the energy of this figure eight. And by following this evolution process, in order for the algorithm to get it correctly, it has to be able to estimate the energy of the figure eight. And given all these caveats that like the gap can only be polynomially small, I want to make sure that at the end, the distance between the energy of this x and the figure eight is either like at least 1 over poly below the figure eight or at least 1 over poly above the figure eight. And so the algorithm needs to be able to estimate the energy of the figure eight to energy 1 over poly. And that's what it needs to do. So let's, and there's one last caveat, and this one's actually quite important, that the x needs to have some sizable matrix element to the ground state on the figure eight. You know, if the figure eight, if I drew some like other really complicated or huge graph, and yeah, the ground state of that graph was maybe some lower energy than the x or whatever, but the matrix element between the x and the ground state was negligible, then the gap would also become small. So, you know, in order to justify thinking of this as a two-level problem, where I focus just on the x and the ground state of the figure eight, I need a good gap between the ground state of the figure eight and the rest of its spectrum, and I need a good amplitude from the x into the ground state of this figure eight. What does that mean? It means that this particular site here, right at the middle of the figure eight, better have a large amplitude in the ground state of the figure eight. So these are the properties I want. That would be what I would need to justify having as a two-level system, and those properties will hold here. So let's ask what the Markov chain Monte Carlo sees, what quantum Monte Carlo sees. Well, initially, so I'll just draw that little picture of trajectories, and let's see. Okay, x will now actually literally be x. Initially, it's just trajectories that are on the x. But then it starts to have trajectories as we increase the energy x that hop over onto the figure eight, spend a little while on the figure, and hop back. And what do they do when they hop onto the figure eight? Well, at first, maybe they spend so little time on the figure eight that they just stay near the middle of the figure eight. But as we start to increase the energy of the x, they have less and less desire to stay on the x. And so they will start to jump onto the figure eight and then wander one way and wander back. And here's an important point. This is a point of topology, that if the particle's trajectory changes only by some local updates, so like its trajectory on its figure eight is some path, and then what it's allowed to do is change the path a little bit, then it's stuck in certain configurations. It can, let me just go to a different color. It could like move like that and move back, or it can move around that way and move back. But what it can't do is it can't go jump onto the figure eight, move around, and come back like that. It can't do a loop around the figure eight because there's no way for it to make a little local change in its trajectory to transition from one configuration to the other configuration. It's stuck. It's stuck doing that. It has this problem that it's only sampling some subset of the trajectories. And how do we describe these topologically distinct trajectories that it can do on the figure eight? Well, a nice way to do it is to write them down as some words. So what we'll say is if the particle does a full loop around the top, I'll write an A. So if the particle does like all the way around the top, I'll write an A. If it does a loop around the bottom, I'll write a B. And you can write a word like A, B, A inverse, B, A inverse means it does a loop around the top, a loop around the bottom, then it goes backwards around the top, goes around the bottom, goes backwards around the top, and so on. So there's actually all these different words. And the number of such words that there are is it's e to the beta roughly, because it's e to the constant times beta. The length of this word that it could do is proportional to beta. And then at each case, it could be an A or a B or an A inverse or a B inverse, subject only to the rule that it can cancel, like A inverse can be canceled against each other. If you wanted to say this mathematically, it's like a word in a free group on two generators. So there's exponentially many such words. So what's happening is that this quantum Monte Carlo, since it's stuck sampling only the identity word and can't sample all these other words, it's misestimating the partition function by a factor proportional to e to the beta. And since the partition function is e to the beta times Hamiltonian, that means it misestimates the energy by a factor of order 1. It gets a very large error in the energy of the figure 8. If you want to say that in another way, and this is important, very important point. So I definitely want questions here because this is going to be important for what comes up later. If you want to say it in another way, what the particle sees is it sees. Oops, let me not draw like that. Okay, we'll go back. We'll draw. Here's the x. What the quantum Monte Carlo sees is it doesn't see the figure 8. It sees a covering space of the figure 8. So it sees something that's, I think it'll be 4 loops. It sees a degree 4 tree coming off. Like this. It sees like an infinite tree of degree 4 going off with lots of little circles on it. Because if it goes around, each of these 4 lines coming out the root are those 4 ways it could go, starting from the center of the figure 8, down, left, down, right, up, left, up, right. And when it comes around in a loop back to where it starts, it doesn't realize it's back to where it starts. So it actually thinks it's moving on the cover of the figure 8. And it's actually sort of a standard result of expander graphs in computer science that the spectrum of this tree can be very different from the spectrum of the 8. What happens is that the spectrum on the figure 8 is the ground state becomes some non-normalizable state on the tree. And if you stick to states on the tree that are normalizable, that sit near the starting vertex, there's a change in energy of order 1. They're quite different in energy from the ground state on the figure 8. So quantum Monte Carlo will mess this up. Now there's all kinds of ways you can change it, open world lines and so on and so on and so on, but there's ways of messing those ones up other. And I don't want to get into that because we're going to have a general way of making all these algorithms not work. But again, let me just pause for questions because there's actually 2 ideas that are going to be used in the general result here. One is this topological idea, like going to that these different sectors are different, and that the quantum Monte Carlo thinks it's moving on the cover of the figure 8. And the other idea is that just moving on the cover means it doesn't know when it gets back to where it started. It just sort of only sees these local rules. It doesn't see the global property that's returned to where it started. And the other property of this specific construction with the x and the figure 8 and turning on and off. So everyone good? Quiet audience. Okay. Please, okay. Okay, what is this? Is there some way of doing, yes, that would handle this figure 8 example properly? Yeah, so, there's certainly, like, you might wonder. And in practice, this kind of problem with topological sectors is something that people encounter in practice. It's usually a milder form where instead of a figure 8, it's a topology of a circle, and then the effect on the ground state energy is not as significant, but it has an effect on other observables. It's something that people encountered in practice, decades ago, long before any of these computational complexity problems arose. And people came around it by doing non-local updates. In many cases, in many practical cases where it was coming from problems in physics, they would figure out some kind of non-local update. They'd realize, oh, I know that I want to go from this topological sector to that one, so I'll just add in a move that directly goes from that to that. So this, as I thought about this problem, I've been thinking about this problem for some years. I had a lot of discussions with people doing Monte Carlo, and they say, well, what about this non-local update? And you'd figure out a way to break that one or break that one. So, Yeah, I mean, so the ultimate result I want to talk about will be a way to break everything within an oracle model. So yeah, for specific ones that are not result from an oracle, and specific ones you can often figure out a way to break it. But we're going to ultimately come up with a way to break every kind of non-local update you can do. How does the energy e to the beta follow, and the fact that it's unity for the covering? Okay, yeah. So what I'm saying here is this is from Eddie. So there are e to the beta, roughly e to the constant times beta, different topological sectors, and that turn out to all contribute roughly the same amount, and you're only sampling one of them. So you get only a tiny fraction of the contribution to the weight that you should when you look at the trajectories that are on the figure 8. So you misestimate your partition function by a multiplicative factor of e to the beta. But the partition function is, in the ground state, the partition function is, e to the minus beta e naught if you're in the ground state. Oops. Let's get rid of that. E to the minus beta e naught is the partition function. Once it converges to that for e naught as the ground state energy. So if you misestimate the partition function by a factor of e to the beta, it's as if you were just off in the ground state energy by 1. Now, what is this about unity for the covering? What I mean is, let's just take a very simple thing. Instead of writing like the figure 8 as the figure 8, if you imagine, the difference between the ground state energy of just like a loop and where okay, so this kind of a general property of let me see how to explain this. This kind of a general property of, so I'm explaining the same thing basically in a different way now. I'm giving a different motivation for the same thing. One motivation for this, explaining why quantum Monte Carlo messes up here, is the idea that you're sampling only some e to the minus beta fraction of the trajectories. But there's another way of thinking about what happens, which is what is the ground state energy between the figure 8 and its cover? And so we can think of the figure 8 as being a graph, right? So it's a graph, and I just have these vertices here and edges between them. And if all the edges have the same tunneling matrix, same amplitude on them, which I will put, say, -1, then the ground state energy is minus the largest eigenvalue of the adjacency matrix of that graph. So we're really just asking, like, what's the eigenvalue of the adjacency matrix of a certain graph? And it's sort of a familiar thing that if you draw some graph that's expander-like, or like locally tree-like even, so I don't know what, you draw any draw like a graph with like a tetrahedron. So it's got 1, 2, 3, 4 vertices and an edge from every vertex to every other one. That would have the largest eigenvalue of the adjacency matrix would be 3. But if you look at a cover of that graph, where now you start looking at something where it's a degree 3 tree, the largest eigenvalue on a degree 3 tree is not 3. It's, if I remember right, it's 2 square root 2. It's a little bit less than 3, and it differs by an amount of order 1. So on a tree of fixed degree, on a graph, on a finite graph of some degree d, the largest eigenvalue of the adjacency matrix is exactly d. But on a tree of fixed degree d, the largest eigenvalue of an infinite tree of degree d, the largest eigenvalue is not d. If I remember right, it's 2 square root d minus 1, but it's smaller than d. So there's a difference in energy. Okay, how does the promise, does that answer the question, Eddie, before I go to the next one? Yes? No? Okay, I'll assume that. Yeah, okay, thanks. Okay, good. So I guess so. How does the promise on sparsity of H relate to K locality? Yeah, so I'm talking about, so when I said H should be sparse, I'm talking about like sparsity as a matrix, that each row has only polynomially many other entries to other columns. So if a Hamiltonian is K local, meaning that it's a sum of local terms, then it's definitely sparse, I guess, like 2 to the K sparse, because you can only change the basis elements on those particular K spins that it couples to. Now, we're going outside the model of things coming from K local Hamiltonians. We're talking about things just coming from this oracle, and nothing is being promised about coming from K local Hamiltonian. These specific ways of breaking quantum Monte Carlo can all be instantiated with local Hamiltonians, but the more general construction, at some point we definitely need to start going beyond something coming from a local Hamiltonian if we want to prove no algorithm can do it, or else we'd be proving a much harder result. So yeah, this figure 8 model, there's a mental change here. Again, yeah, is this figure 8 model K-local? There's sort of a mental change in how you should be thinking about things. Instead of thinking about things as like these basis state of n qubits that are to the n basis state of n qubits of strings of zeros and ones, and K-local Hamiltonians that act on strings of them, just think about some arbitrary basis of computational basis states and some Hamiltonian which is sparse in that basis. And I'm just going to draw like graphs to indicate where non-vanishing basis elements are, non-vanishing matrix elements are. Sorry. So instead of picturing everything in terms of being like a K-local Hamiltonian, think in terms of a think just in terms of like, oh, Hamilton, like, you know, just matrices with like rows and columns and some promise on the sparsity, sort of the change in mental image. So yeah, we could instantiate the figure 8 with a K-local Hamiltonian. Actually, Sergei Bravy and I did something similar to that when we were showing some power of Ising model with transverse field, that you can instantiate a lot of it. We built a lot of gadgets to instantiate a lot of these things, related things. Okay, so this is a way to break quantum Monte Carlo, but it doesn't Markov chain Monte Carlo, quantum Monte Carlo. It doesn't break, you know, all algorithms. There are other algorithms that will work on this. But I'm going to try to, in the remaining time, sketch how we prove that within this Oracle model, no algorithm can work. So we're going to actually use the same kind of general idea that I'm going to draw a graph. You know, it's going to have some vertices and edges. In the previous case, it was the figure 8. It'll be some kind of funny graph, whatever, with some vertices and edges. And I'm going to draw a single extra site, and I'm going to draw a dashed line between them. And I'm going to imagine a sequence where I start with that dashed line having 0 matrix elements on it. All the matrix elements on the graph will just be -1 where every vertex is. So the eigenvalue on the graph will be minus the adjacency matrix on the graph, minus the largest eigenvalue of the adjacency matrix on the graph. And I'm only going to change 2 things, the x and the dashed line. And we're going to start with a very negative energy on the x, then we're going to increase the coupling on the dashed line, increase the coupling on the x, and then turn off the dashed line. And whether the particle ends on the x or ends on the graph will depend upon how the largest eigenvalue of the adjacency matrix of the graph compares to that of the x. So in order to be able to determine whether it ends on the graph or on the x, it needs to be able to estimate the largest eigenvalue of the adjacency matrix of the graph. Now, this isn't exactly what I said at the beginning as the Oracle problem. There's a couple other steps. For example, I said that at the end of the evolution, the ground state would just be a single basis state. And now if it ends on the graph, it's actually a superposition of states on the graph. Also, in this model, there's a very easy way to determine, you know, with at least 50% probability what the answer is. You just sort of randomly either pick the x or the graph, and half the time you're right. So it's a little bit of a different model, but there's a few gadgets that I'm not going to go into where you can show that you need to be able to solve this model in order to be able to solve the other one. You can construct something out of copies of this such that you need to be able to solve this problem well in order to be able to solve the other one. I'm not going to go into that. That's in the paper, but I'm just sort of going to at this point skip and say, yeah, in order for the algorithm to be able to solve the problem I originally mentioned, you need to be able to solve this problem where there's a graph, there's an extra vertex with it, which is an x, and there's this hopping between them, and you need to be able to estimate the ground state, the largest eigenvalue adjacency matrix of the graph. Excuse me. So what are the properties of the graph that we need? The properties of the graph that we need is the graph should be only polynomially high degree. The largest eigenvalue adjacency matrix should be separated by at least 1 over poly from the next largest eigenvalue of the adjacency matrix. And there's one last property, which is very key, that the eigenvector on the graph with largest eigenvalue should have some amplitude on that vertex that's at the other end of the x. Excuse me, sneezing here. So some amplitude on this vertex here, some at least 1 over poly amplitude on that vertex here. And I'm going to call this vertex the start vertex, that one vertex here. So there's a graph that has a privileged vertex called the start vertex, and there should be at least a 1 over poly amplitude of the ground state on that. And skipping over a lot of steps, you can sort of see that this is intuitively like a cartoon picture of the adiabatic evolution. If I just gave you a graph and asked you to find the largest eigenvalue of the adjacency matrix, this would be hard. You know, maybe there would be like this whole graph, and there'd actually be a disconnected vertex somewhere far away, and that vertex, well, some disconnected component far away, and that disconnected component had very high degree, and it turned out that that was where you should be looking, but you're looking in the wrong spot. That you would have to really exhaustively search the graph. But you're given a promise, you know, just like, you know, instead of doing find the ground state energy of an arbitrary Hamiltonian with no sign problem, it's, oh, we also get adiabatic evolution. Here, the analog of getting adiabatic evolution is you get a start vertex that has some amplitude onto the ground state. So you get kind of a clue. So the problem is, given this graph, estimate ground state energy, given this promise on adjacency matrix and given a start vertex. And the construction to prove that there's no way to do it will involve coming up with an oracle model in which there's no way to distinguish them with bounded with n log n queries. So we're going to come up with two different graphs. One which will have a different largest eigenvalue of the adjacency matrix, a sizably different largest eigenvalue of the adjacency matrix, at least 1 over poly, but you can't distinguish the graphs with a small number of queries. So the classical algorithm can't do it. A small number of classical queries. You can do it with quantum queries. You have to be able to. Quantum algorithm works. Running a little lower on time than I thought, but I guess it's probably okay if I go a little bit over, hopefully. Let me let me talk about the first idea to do this. So we're given this graph, and what we're going to do is we're going to so one thing it's kind of like an old result. Actually, it's like I think it turned out same lemma as in Andrew Child's old paper on glued trees, I believe, that basically within this model, we can assume that your queries to the oracle are only queries of states you've already seen. So that the algorithm starts by querying the start vertex. It gets a list of other vertices, and actually it's just querying properties of the graph. So it just gets the neighbors of the start vertex. And then it can pick one of those neighbors of the start vertex and query what its neighbors are. It can pick one of those neighbors of it, and so on. So actually within this setting of the graphs, you don't even really need to worry about how S changes. All the algorithm does is it just starts at the start vertex. It can query for its neighbors. It can pick any neighbor, query for its neighbors, pick any neighbor of that, query for its neighbors, and so on. You should never just pick a completely unrelated vertex. So you should never say like, oh, okay, I've queried vertex 0 and its neighbors were vertices 1, 2, and 3. Okay, tell me what the neighbors of vertices 10,723,000. You can assume that the algorithm never does that, because there's a little trick. You can make it so that most of those queries are useless. So you can just assume that you only make queries of vertices that are neighbors of ones you've already seen. Now we're going to make one extra trick. So let's say we have some graph, right, with some vertices. What I'm going to do is I'm going to take each vertex and I'm going to blow it up into a lot of little vertices. Okay, I'm going to do this for every vertex. Each vertex is going to be blown up into a lot of little vertices. And for every edge in the graph, so there's an edge between like this one on the top and then this one down here, I'm going to replace it with lots of edges between those little vertices. So there'll be edges between those little vertices. Okay. And there'll also be within each of these blown up vertices, there'll be hopping terms, I'll draw it in one more color, between all these little vertices. Okay, so all the little vertices in the graph. Now the hopping terms between all the little vertices in the graph will be chosen so that the ground state is very well described by something that's just the, like on every big vertex, you take the uniform sum of all the little vertices on that big vertex. So we'll have this strong hopping between the little vertices on each big vertex, so that when looking for the ground state, we can just assume that, oh, on every big vertex, we're in the uniform superposition of all those little vertices. And then each of these red things that I drew, these red edges that are the coupling between the little vertices, we're going to couple a little vertex in one to a little vertex in the other, but we're going to do it with an arbitrary permutation. And on every edge, we'll pick some permutation. So just little vertex here, we'll couple to a little one here, and we'll choose those permutations at random. So what's the effect of doing this? From the point of view of the quantum algorithm, the effect is nothing. Or when I say quantum algorithm, I mean we just describing like the eigenspectrum of this graph. We assume that we can work just within the space where you're in this uniform superposition of all the little vertex on every big vertex. And then this random permutation doesn't affect it. You just hop from this uniform superposition to that uniform superposition. But let's see what happens when you put this random permutation in, but you do the classical algorithm. So if you were doing queries on the classical algorithm before, and say I had this triangle, if you did what originally just the triangle, you start at the, let's say that's vertex 0, and you say, what are its neighbors? And it would say these two. And you'd say, okay, well, this vertex, what's its neighbors? And it'll give you this one. You say, this vertex, what's its neighbor? And you get that one as a new one. And you go all the way back and say, oh, I've just done a loop. I see that I followed a loop. And you just identified that there's a loop here because you would have noticed that you returned to a vertex you'd already previously seen. But now when you're querying with these little vertices, you'll start with some little vertex. You'll get a hop to a new, you'll hop from somewhere up here to somewhere down here, but you'll hop from one of the little up here to one of the little ones down here to another little one down here to another little one down here, and it'll be a composition of all those random permutations. And choosing there to be exponentially many little vertices in each big vertex, you can make it exponentially unlikely that you ever return to where you start. So the result is the classical algorithm doesn't know where it returns to where it starts. It only sees the cover of the graph. It doesn't get to determine when it returns to where it starts. And it will know when it returns to the start vertex, because when it returns to a copy of the start vertex, but it otherwise can't distinguish when it returns to where it starts. If it hops around the loop, it doesn't know it hops around the loop. So now let me give the construction. So that's the first part, and that's key. It's just like how we were tricking Monte Carlo, but now we're making it so there's no way you can know about the loops in the graph. You always think you're moving on the cover. So now I'm going to make graphs that can't be distinguished well. I'm going to draw sort of a rectangle like this, okay? So I'm going to have a rectangle that I'm drawing here. And it's going to have some length called L in this direction and some length little n vertically. And the coupling on this rectangle is going to be every vertex in each column will couple to every vertex in the neighboring column. So I won't draw all of them, but like that one. Getting pretty crowded, right? I shouldn't probably have drawn all these. And then these last ones down here. So they'll be, yeah, if the larger graph is only a constant number of the vertex, can't the classical algorithm remember which vertices were in which cluster? So first of all, okay, the larger graph is actually going to be polynomially many vertices. But the other thing is you don't know which vertex is in a cluster. What you're querying is you're just getting labels. You're just getting labels of vertices. So you just get a basis state, you get another basis state. You don't know that you return to it because the only thing you know when you're at a vertex is you get to see the neighbors of the vertex, or you can ask them neighbors of neighbors so you can learn more about it. So really, you're in this very limited setting where you're moving on a graph, and every time you come back to the start vertex, you get told, oh, you just returned to the start vertex again. But otherwise, all you get to know is the neighbors, is the degree of your vertex, is the degree of the vertex, and then you can ask for the neighbors, and you can ask for the degrees of those neighbors. But even if it's, you can imagine that if it's something you've already seen, you just get a new name for it. So if you're here, you hop to here, you hop to here, and you are back to hop up to there, you just get a new name for it. So you're like, I'm at vertex A. Oh, okay, here's vertex B, that's a neighbor. I'll query, oh, C's a neighbor, I'll query that one. I'll query that, oh, here's neighbor. Now, it really turns out you're going back to A, but the oracle just tells you, oh, that's vertex D, it's just a new one. So you get a new name whenever you come back to it. So you have to work out properties of the graph. But you only get this very limited information. And the question is really, can we make a graph so that with this limited information where all you get to know is degrees of vertices, and then you can ask about its neighbors and ask the degrees of those neighbors and so on. Can we make it so that it's impossible to estimate the ground state energy? You don't get to know which one is in which cluster. You don't know when you return to a cluster, because that's the whole point. It's exponentially like it's almost certain that it'll be a new name for it when you return. And I'm going to take this graph, and the start vertex is going to be somewhere in the middle. It's this thing, start somewhere in the middle here, and there's more columns over here. And I'm going to either attach the left end to the right end in the same way, or not. I'm going to do that. Those are going to be the two different graphs, almost the two different graphs. We're going to have to do a little bit more stuff. Now, it's a standard estimate that that this is a degree. The degree of this graph is n. 2n, I guess. Everything couples to two little n here. So if I couple the left edge to the right edge, it's a regular graph of degree 2 little n, and the largest eigenvalue will be 2n. And it has to get 1 minus something like constant over L squared if you don't connect the left edge to the right edge. So if n and L are only polynomially big, then these two graphs exactly fulfill the requirement that you have a 1 over poly difference in energy between them, that you can easily check that the start vertex has a 1 over poly amplitude onto the ground state. On the other hand, you can also efficiently distinguish them. It's not yet the counterexample. I'm going to get to the counterexample because there's one more idea. So how do you efficiently distinguish them classically? You start at the start vertex and you just keep querying neighbors. And after And what you'll be doing is you'll be doing a random walk left and right. You won't know where you are, except every time you return to the start vertex, you'll see it. But otherwise, you basically don't know where you are. And the question is like, eventually, after roughly L squared steps, this random walk will hit the left or right edge. So the simple classical algorithm is like do 100 L squared steps. And if you ever see a vertex with the degree less than 2n, like you see a vertex of degree n because the left and right edge weren't connected, you know you're in the one where they're not connected. And if you never do, then you're almost certainly in the one where they are connected. So there's a simple way to distinguish it, because if you just keep walking, you'll just eventually hit the left or right edge. So now what I'm going to do, though, is I'm going to make it a little harder. On every single vertex, I'm going to attach a tree. This is a procedure called decorating the graph. So we're going to attach a tree onto every vertex. And the tree is going to go for some depth that I'll talk about. So every single vertex, we attach a tree like that. All the trees will be the same, and they'll all have the same degree as the original graph. So now when you're walking, you can't tell whether you're on the tree. Okay, so you can do this in roughly L squared steps. Now when you're walking, you can't tell whether you're on the tree or whether you're on the original graph. And this is crucial because you can't see that there's loops. If you're on the original graph, you can see, oh yeah, I know that like I'm on a vertex, and even in a very small neighborhood of where I am, there's a loop. And so if you could like detect that you were going around loops, you could, in a very short number of things, to tell if you were on loops, and there would be a modified algorithm. The algorithm would be, do a random walk, but always check that you're near a loop. And if you're not near a loop, you know, try something else, and then see after 100 L square steps if you're there. But now there's no way to tell if you made this false step onto a tree or not. And so what do you have to do? You have to keep going. And after some number of steps, well, if we made the trees really deep, you could get lost in them and keep going. But then you'd say, well, after a huge number of steps, maybe I'm on a tree and I shouldn't have been there. You might try going back and trying something else that's not on a tree. But let's make the trees, just to make it a little easier, let's make the trees only like of order little n deep. Now, half your steps wind up being onto a tree. And you have to, your time gets multiplied by a factor of n. Because half the time when you take a step onto a tree, and you don't notice it until you've taken, or let's make the tree, sorry, of order L or something like that. They're all polynomially related to each other. Half the time when you take a step onto a tree, and you don't know that anything's different until you hit the end of that tree. And that takes roughly n steps to do. And then so you take all these steps on the tree, you know, you're going like, oh, okay, oh, I hit the end of a tree, that was wrong. Let's try another step. So let's try another step. Let's go different colors. Try a step on the graph. And oh, I went on another tree. Oh, that was wrong. Let's try another step on the graph. Okay, good. Oh, I stepped on the graph. Oh, now I did another step on the tree, and so on. And you don't know that anything's wrong until you hit the end of the tree. So this makes the time take polynomially longer. Let's just keep going. We'll just, on top of every tree, every vertex of this thing decorated with trees, we add more trees. So now when you're stepping on the tree, half the time you drop onto one of those subtrees, and we make it take even another factor of n, and another factor of n, and another factor of n. And we can build up all these factors of n. And it turns out every time, I see a question I'm going to answer, but let me just finish this thought. Every time we add a tree, you double the number of, double the degree. So we only get to add trees log many times. So we get to get this n to the log n factor. Oh yeah, how do you know which node to backtrack where the tree started? Well, you don't necessarily. You know, the question is like, I don't know what the best classical algorithm is to solve the thing with these tree vertices. So I'm going to give even the classical algorithm a little extra help, right? If I give it help, it doesn't. If I can prove a lower bound on the number of queries needed with this help, I've proven a lower bound on the number of queries without this help. So I'm going to give the classical algorithm a little help. And so there is a proof in the paper that proves that no classical algorithm can do it, because you really need to make sure that, I've sort of intuitively said, oh, you can't tell the difference between this tree and this one, and you need to express that in terms of differences in probability distributions and so on, to make some formal statement of it. But so I'm just speaking heuristically here. Yeah, of course, you might not always know exactly how far to backtrack, and you might backtrack to the wrong one. But the point is that even if you give it all this extra help of like telling it exactly where to backtrack to when it hits certain things and so on, which makes the proof much easier, because then you can immediately see certain things. Oh, well, the optimum algorithm, when you know where to backtrack, is to exactly jump back to this point, and then you can bound the difference between certain distributions of whether or not you're on the tree, so you can prove that it can't know whether or not it was on the tree. So like half the steps are a step from the base graph to the tree, and it can't know when it did one or the other. So better than like a probability 1/2 minus some like exponentially small thing, unless it spends a lot of time walking on the tree. So yeah, I don't actually know what the best algorithm is, but I'm just giving the heuristic picture of like, with this extra help, that's how well it can do. So now this model of a tree may seem, let me just give one last thought and then I'll close. Sorry, I went a little bit over. May seem, very what is going on here? You know, I'm making some use of the inability to tell what's happening with loops, but what are we doing by decorating with trees? Well, there's another interesting algorithm. You know, I said Markov chain Monte Carlo was the premier algorithm for simulating this kind of thing, but there's another very well-used algorithm, diffusion Monte Carlo. Diffusion Monte Carlo is another classical algorithm for simulating this kind of problem. And the idea is that you have a collection of walkers. Each walker is supposed to be sampled from with a probability that's proportional to the ground state wave function, not the wave function squared, but the wave function amplitude, not the square, but the amplitude itself. And then you have an update where each walker can sort of hop from one site to a neighboring site with a probability that depends upon that off-diagonal matrix elements. And then also, as walkers are on sites that have some diagonal matrix element, there can be a birth or death process. So if the walker is on a site that has a large energy, there's a chance that the walker just disappears. And if it has a site that has a negative energy, there's a chance that you can create new walkers on that site. And you can set up the equation so that the density of walkers is correctly, you know, obeying the Schrodinger equation, so that they'll be sampled from them with the right probability. Unfortunately, it doesn't always work. It can be subject to large fluctuations and be unable to appropriately equilibrate the population with a polynomial number of walkers in a polynomial time. But one of the key ways you might guess that there's a problem with this, and this is, so Jordan and Lackey and one other worked on this, I don't remember the other one, is that this model, as I said, it's sampling with a probability that's proportional to the wave function rather than the wave function squared. And this is a little weird, right? The wave function squared is the physically meaningful quantity. So if you had a quantum Hamiltonian where the square of the wave function was concentrated on some basis states, but the wave function was concentrated on some other basis states, it would be sampling the wrong thing. That is, a few basis states with a large amplitude and an enormous number of basis states with a small amplitude. If you sample from the norm of the wave function, you might be sampling from over here, the large number with a small amplitude. And if you sample from the square of the wave function, you might be from the small number of ones with a large amplitude. And this particular tree graph construction here has the property that the the norm square of the wave function, you have to play around and set up all the constants, right, is highly concentrated on these nodes that I wrote at the beginning, all these ones at the start. It's highly concentrated there. That's where the norm square is, because all these trees we've added a huge number of vertices, but they have roughly speaking, have a higher energy on those vertices. And the norm square of the wave function is still concentrated on the stuff where you started. This is using the fact that the energy is higher on the tree and so on. But the norm of the wave function is actually highly concentrated on the trees. And so we've set it up so that this diffusion Monte Carlo would fail. But essentially it's an Hamiltonian that's been set up so that we sort of forced everything to basically do diffusion Monte Carlo on this, because however it queries, everything looks the same locally until it hits the end of a tree. So all it can do is kind of randomly walk out, and it winds up getting forced to query a lot of the nodes that are not the ones where the wave function is concentrated, ones near the end of the tree. So let me just stop and take questions. I guess you said you want to have also discussion after. So yeah, thanks. That's the main result. Let me say one more word. I'll say one more word. Sorry, a little disorganized talk. This is an oracle result, as I said. I think, oracles are, it does mean that there may be room for an algorithm that works for local Hamiltonians, but I think we could also take another view of an oracle result. So Simon's algorithm is a famous result, Simon's problem, that gave a separation between quantum and classical computing relative to an oracle. I think an exponential separation. It's relative to an oracle. But if you pick a specific choice of the oracle, you get Shor's algorithm for factoring. Now, there's no proof that there's no fast classical algorithm for factoring. It's strongly conjectured that there's no fast classical algorithm. There's no proof. But you can start with this oracle problem, and you can make a specific choice of the oracle and get a very useful algorithm. So here we have at least some evidence that with respect to an oracle, well, we now know with respect to an oracle, this problem is more powerful than classical computing. We don't know how much more powerful. It's super polynomial, but it's barely super polynomial. There's still a lot of room to potentially either, push the lower bound to higher things, or, maybe come up with classical algorithms that are faster than exponential, even if they're still super polynomial time. But at least it's a super polynomial separation. So the question now is maybe like, can one come up with an instantiation of this oracle? Can you really make up, it's not going to just be a driving term plus and some arbitrary objective function from some optimization problem that you care about, but maybe some very structured kind of thing that uses this ideas of differences between having loops and not having loops or something like that. Maybe there's some specific instantiation of the oracle that can be a useful quantum algorithm. So, okay, let me end there.
Thanks very much. Yeah, so maybe if people have more questions about the talk, maybe type them into the chat window, and we'll see if we can take a few more questions quickly.
Yeah. Okay. I think a larger separation is possible? That's a really good question. That's exactly what I was saying at the end. I don't know. Initially the setting was that something could have been polynomial classical algorithm, or it could have been exponential. Now it's been pushed up a little bit. The lower bound is n to the log n. That still leaves a lot of room. I mean, that's one of the signposts where we get interested, is that something is super polynomial. Another interesting signpost is like, is it exponential or sub-exponential? This is something I really don't know. I mean, to be honest, initially my feeling was that there was going to be a classical polynomial time algorithm. So I don't know. I would sort of hope that maybe this sort of formalism of looking at graphs and looking at subject to these requirements of the start vertex having 1 over poly amplitude, that might be more useful way to prove more general separations. But I can also start to guess some classical algorithms that might involve some clever sampling, where there might be a classical algorithm which sort of like, say, starts with a vertex and locally solves something around it by brute force over some exponential time, and then uses that to inform its walk on the graph. So yeah, it's an open question. I would love if someone could make some progress on that.
All right, thanks very much. So let's end the talk here, and then we'll switch over and have some informal discussion.